Okay, I'm recording. And so we'll probably wait for a second for everyone to find the new link. I think what I did is a few days ago, I noticed this was running out, so I tried to extend it a little bit farther in time, and it reset some of the parameters. And so I just reset it again, but I didn't know if the link had changed. I can probably just see that here. Let me see. My meetings previous.
Yeah, somehow meeting changed, link changed.
The link had changed? Okay.
I think so.
I was messing with it and I screwed it up and then I fixed it and it was a different link. I saw Ian was trying to get in just as I closed out the last one. So we'll wait just a second there.
I'm setting that back.
And Britt's going to be late. You probably got her.
Yep, I saw that. That's totally fine, of course. Oh, looking for my stuff here.
Okay. Nice haircut.
Thank you. Yeah. My wife insisted yesterday, so there's Ian. Good. Sorry, Ian, I screwed up the now I'm having mouse problems, of course. Nothing's
It's a bad tech day for you.
I know. It's my brain's not functioning anyway today. I'm just like tired. I can't seem to wake up. I haven't had coffee yet. I think that's the problem.
Are
Yes.
you feeling better?
Oh yeah, I'm feeling good. I was sick for a while, for like a whole month. I had bronchitis or something, but yeah, I'm all good now. Y'all doing okay? Surviving?
Yes. We
Okay.
have also got that, but yeah, it is now better, much better.
Well, let's see. I am recording. Good. Yeah, I was saying, Ian, I stupid mouse. I tweaked the Zoom settings, trying to extend it a couple weeks because we're going a little bit longer than I thought, and in doing so, I messed up the settings, and so when I corrected the settings, the link was different, but we all seem to have found it, so good.
Yeah, it looks like it reset the password.
That's it. The link's the same, but the password's different. Okay, yeah. All right. Well, first of all, thanks for the week off. Last week, I got my DoD report out. Here, I'll just go to sharing mode right now. And I sent it around to you. I don't expect you to read the. I'm just going to unplug my mouse so I stop trying to use it. Use my mouse pad. And put you all over here so I can see you. Okay.
Window is small somehow. Is this?
Oh, did I?
Everybody? Oh, maybe.
Did I not share correctly?
Me only. Sorry, it's resolved.
It's resolved.
It's only me because my window was minimized. Yeah.
Okay.
Sorry.
Technical problems all around. It's the theme today. Right. So the DoD report. It's 42 pages. I don't expect you to read it all or any of it, but it's just if you're interested. This is for the MW curriculum, which I'm hoping that after you offer OPIS, many of you join that effort. That's where all the other OPIS educators are. We have these wonderful meetings. It's currently like 3 of them per week with the educators. And we talk about all sorts of cool stuff, and it's just an enjoyable community. But the DoD report, we have to do quarterly reports, but this is the annual, so it covers everything for year 2. As a good summary of the modules, in year 2, we finally settled on the curriculum. Last time I showed you the HR diagram, but there's lots of modules, introductory ones with the solar system, optical, and radio. Then we get into astrophotography, Stromgren sphere calculations, radio astrophotography, star death regions, gravitational wave. We have a pulsar unit for neutron stars, gravitational wave unit for black holes. Then we get into galaxies, starting in the radio with all sorts of Doppler stuff. And then kind of capstone optical radio. And it's a fun unit. Maybe I'll just pause here and mention kind of the capstone thing that we do in MWU. I don't think I mentioned it to you before. By now, they're all experts at making really awesome pictures. This is prompt optical, but also Spitzer in there. And they all hit different types of galaxies: normal, spirals, starbursts, Seyferts, radio galaxies, ellipticals. And from their optical image, well, it's optical, it's H1 spectroscopy in the radio, which we'll learn a lot about today. They can say, oh, does it have cold gas from the radio spectrum? Does it have dust from their picture, blue stars from the picture, star forming regions which glow in H alpha in their picture, warm dust, star heated dust, and we get that from Spitzer. And so they have kind of a qualitative measure of star formation, and then they do a radio map, seeing if there's a synchrotron source. Is there a supermassive black hole at the core that's gobbling stuff up and spitting out radio jets? And they put their galaxies on this plot, and then they work, teams combine, and they say, okay, you put yours here, I put mine here, and they make adjustments relative to each other, and then teams of teams combine. And it's a very qualitative process, but they end up putting all their galaxies in the different parts, and then you can walk them through galaxy evolution. We, of course, can't see galaxies evolve, but you can see like a normal spiral, and then you see a small merger, which gives you radio emission as a Seifert, and then you end up with a larger spiral. So that's one evolutionary cycle with galaxies. Or you can have a major merger, which gives you just a mess. Gives you strong radio jets that calm down and give you an elliptical. The mess settles down into an elliptical. So kind of a class-wide activity where all the different groups did a different case study, and it all comes together into this picture of galaxy evolution, which is kind of fun. Anyway, I wasn't planning on going through that. I'm just kind of scrolling through this document. Made a lot of progress on our gravitational wave interface, and this can be used, without Skynet telescopes. We directly load data from the LIGO site, and it creates the same data products LIGO does, which is challenging. The code base, we've mastered the LIGO code base, and then they can fit total mass and mass ratio and distance, matching the strain models and their frequency versus time spectrograms. And we currently have an MW group building a module all around that. So, and then there's some more about new things we're doing with the HR diagram tool. So I noticed some of you have been emailing me. I'm trying this one, I'm trying that one. So I just love the enthusiasm. You're not even in the MW group, and you're here following these links and trying some of the activities, and it's wonderful. We go on and talk about kind of the software behind the scenes stuff, what's going on Skynet 2, the new Astromancer site, our hardware effort with the radio telescopes in Australia. In fact, the guy who's building the signal processing units will be here next week, and I'm taking him to Green Bank. We'll have our next meeting. When we have our next meeting, I'll be at Green Bank. And then it ends with some of the education research stuff with MWU and boilerplate stuff. Anyway, lots of info there, and you're welcome to peruse it, and you're welcome to try some of the MW activities. And if you need more telescope time to do it, just let me know. So there's that. Other announcements. A couple weeks ago, we talked about Argus. I told you how this is the coolest thing ever, and I won't go through all of it again. That's my phone. I won't go through all of it again today, but I'll just announce it's now funded. We got our $24 million of private funding. And so we'll be building this thing over the next, probably 3 to 4 years. It's a rapid construction timescale. And by we, I mean my colleague, Nick Law, though it appears I'm going to be playing a large role in a couple of things in the education aspects. So, we have this large education group. You're just being introduced to it through OPIS. There's the MW effort, but there's going to be all sorts of education efforts tied to this thing. There's no machine better ever for tracking variable stars, finding transients. I'm hoping to build a Skynet cluster right next to it. So as it finds things on its 1 second cadence, it can get down to 16th magnitude in 1 second. It can process that data, difference it in 1 second. My mounts are overpowered so they can salute at any point in the sky in 1 second. So by second 4, I'll have telescopes doing follow-up at other wavelengths. And of course, this thing keeps observing. And it's just going to be, scientifically, I'm going to be chasing the 1 second sky using this as the trigger. But educationally, with all the variables and transients, we'll build tools like the ones that we've been building for OPIS and MW and write multi-million-dollar grants around it. And so I'm very excited. And this creates a lot of opportunities for us as educators, as well as the obvious scientific opportunities. So funded, hooray. Only other announcement is the standard. I've posted the video from last time. Here it is at the bottom, taste of MW. We did some more OPIS Lab 5 stuff, and we did Lab 6. And today we're focused on Lab 7. So questions about any of that or about anything else? Yeah, Brett.
Hi, Dan. I just tuned in, so I tuned in late. I just wanted to know, we're putting in the observations for the radio telescope today. Yeah. Did you say something about that? Is it functioning? Will it work?
Yeah, so I sent an email shortly before. So short story long, as is my tendency. And you don't need a lot of time. 1 second is enough to get this data. But the processing, at Green Bank anyway, they have problems processing 1 second observations. And so a couple of years ago, I changed it to 2 seconds, and it still is creating problems. Most of the time, the observations go through, but sometimes the system gets jammed up. And so I'm now recommending that everyone try 5 seconds. I just sent an email around, and if you're just putting the observations in, try 5 seconds. And we flooded the system at Chapel Hill doing Lab 7 they put their observations in last week, and telescope's been going down a lot. So we'll try 5 seconds. Now on the optical side, we have what's called linking. If we have a bunch of people who put in the exact same observation and it's at the top of the queue, we do it once and they share the data. Linking doesn't work on the radio side, and we're not going to add it because we're building Skynet 2. It's already there in Skynet 2. So imagine 3,500 students all putting in 1 second observations, and now we're going from 2 into 5. So now it's 5 times as long. That time actually builds up and starts approaching our limit of what we have on the telescope. That's why I've been trying to keep it small, but if it keeps breaking the scope, we'll go longer. So anyway, short version, yeah, despite what the videos and labs say, use 5 seconds. Let's try that. That doesn't work. We'll try 10.
That sounds good. And then going back in time, I tried to do the asteroid a few weeks back, and I almost had it. I got one of the telescopes, but the other one it never downloaded. We had just gotten back the Cerro Tololo, so I don't know where those images are.
Yeah, so I just learned yesterday, prompt 5 is carrying out observations but not returning the data. Was your observation marked complete but not archived?
Yeah, well, I don't know if it said archived or not, but it said complete, but I couldn't get like a preview of it, and I didn't see it in the afterglow.
Complete means it took the data, but it didn't transfer it back. My programmers became aware of this yesterday. They should have fixed it, and you may want to check it and see if it's caught up. It has a couple weeks of data to transfer. There's a little program that transfers the data, then it's marked archive. Apologies, but when the site goes down for 77 days, and when it comes up, often there are going to be little snafus along the way. So it sounds like you got your data, and it may actually be there now. If not, it should be there within a day, I would think.
Oh, that's great. So I shouldn't try to repeat. I was going to try to repeat that one because I've not gotten it yet, and I wanted to try to get the asteroid, but I won't do that if maybe
Yeah,
I've already got.
Yeah, the data. If you don't have it yet, it's either because my programmers haven't turned the data transfer service back on, or it's just working through a backlog.
Okay.
Fortunately, prompt 5 is small images, so we should be able to catch up pretty quickly.
Okay, and one last question about if I wind up taking an observation of something that people weren't able to get themselves, what's the permissions on the folders so that I could make it available to all the students? Like, where would be a good place to put an observation maybe that I make for everyone, other than the one we've already discussed?
Completely open. So if they go into Afterglow, instead of going to user observation, they'll go to group observation. Then they'll go into your folder, and you tell them what observation to grab.
Okay.
That's how we do it right now. It's actually not good because the science people want their stuff to be proprietary for a certain period of time. In theory, rivaling scientific teams could find each other's data. And so in Skynet 2, there's going to be a much more elaborate permission structure where you can turn things on and off. But right now, the whole thing's wide open.
Okay.
They just have to navigate into your folder instead of theirs.
Thank you.
And if that becomes too problematic, we can always put stuff in the sample directory, though I'm kind of reluctant because it has to be done by hand. It's a bit of a mess, but anyway. Any other questions? Okay, let's move to lab 7. Let's see. So I've already downloaded it. It's here. Okay, lab 7. And I didn't prep anything, so I'm looking at my notes, and we're just going to bumble through this. So here we go. Let's see. Right. So at the top here, we have our standard 3 videos. In fact, I was on this page before it. No, it's now this page. The standard 3, the introduction, an overview of the background sections, which is pretty lengthy. That's something I'll come back to. This is a background heavy lab, and the procedure, which is actually fairly straightforward. And then we have 3 how-to videos embedded deeper down in the lab, including some more on using spreadsheets. The observation planner, you can go there, but there's no observations to put in for lab 8. So there's nothing to submit this week. That's good. That saves you a little bit more time to go through background material. Standard comment, they should go back and check the solution set, particularly for sources of error from the previous lab, so they continue to learn. And then into the lab. I should say, even though we don't have to put observations in for lab 9, if we go to the observation guide, it does tell them there no observations, but there are some supplies you need to round up. So let me go through that just briefly. Lab 9, I'll go to the supplies here, equipment. Lab 9 is, sorry, I'm saying lab 9. This is lab 8. I'm about to write lab 9 that's a follow-up to lab 8. So lab 9 is Hubble's Law, understanding Hubble's Law. It's one of our 2 labs where they don't actually acquire Skynet data. The other was lab 2 to understand the seasons. Both of these labs are designed to correct common misconceptions. With the seasons, why is it hotter in summer, colder in winter? Big common misconception. And this one here is with the Big Bang. What is the true nature of the Big Bang? And there's big misconception about it. Everyone thinks that in the beginning, space was there and vast and empty, and all the matter was concentrated, and you had a traditional explosion. And that's not what happened. And we'll go through all this next time, but space has always been pretty uniformly filled with matter. It's just space is expanding, carrying everything away. And this is to help them understand that. And we even touch on dark energy here. But anyway, it's a manual lab using very basic supplies. I rather like this lab. Seems a little gimmicky when it's push pins and rubber bands, but it does a good job. We have this one-dimensional expanding universe, and we do decelerated expansion and constant expansion and accelerating expansion. And from measurements off the rubber band, they produce Hubble's law, cosmological redshift versus luminosity distance. And they can see how it curves in a or accelerated universe. Anyway, supplies. If your students are online and remote, they have to find the stuff themselves. But if you're doing it in class, it's inexpensive stuff. It's not like Lab 2 where you have to buy globes and, well, if you're doing the globe version, globes and ring lights and PVC frames. And this is inexpensive stuff. You should be able to round this up. Rubber band is the key thing. It can't be any rubber band. When you cut it, it needs to be at least 18 centimeters long. It's still it's a easy to find standard rubber band. So when it's closed loop 9 centimeter or bigger, it shouldn't be a thin, cheap ass rubber band, because they're going to be stretching them, putting tacks through them. They can rip and tear. So a nice, rubber band. You can see here from the picture kind of what I'm talking about. Scissors to cut it, ruler to measure it, just a regular 1 foot ruler, but with a centimeter scale, is as much as we stretch these things. Marker, we end up putting 5 evenly spaced galaxies on here, and something to stick it into, either foam board or thick cardboard or bulletin board, and push pins. So those are the supplies for Lab 8 that you want to gather in advance. And we'll come back to this next week. Okay. So what are we doing in Lab 7? I'm just finding the place in my notes here. Supplies, goals. Okay. Goals of Lab 7. This lab is unique. It's different from all the others. I'll get into the reasons why in a second, but the goals here, they're going to learn how to measure speeds at which gas, moves and orbits the galaxy. So Doppler effect stuff. They're going to measure the rotation curve of the Milky Way, standard, fundamental concept. We teach rotation curves in our introductory courses. So they're going to actually measure the rotation curve of the Milky Way. And by looking at this curve, they're going to determine if the mass is centrally concentrated. Like in the solar system, you get a Keplerian rotation curve. With galaxies, you tend to get flat rotation curves. They'll get a flat rotation curve, which means the mass is not centrally concentrated, but spread out. You know this stuff, but you'll see it again in the background sections in just a moment. And then once they have the rotation curve, they're going to measure the mass. The rotation curve is speed as a function of distance from center of galaxy. If you have those two numbers, the speed and the distance from the center, you can calculate the enclosed mass for each of these different radii. So they're literally weighing the galaxy. They're going to take 12 spectra, just a few seconds per spectra, and they're going to weigh the galaxy with just seconds of data, which is kind of cool. And we even throw in LMC and SMC, even though their distance and speed have to be measured in other ways. We just kind of give them to them with the distance from the center and the speed. Allows them to extend the rotation curve and the mass distribution out. And we can talk about dark matter. So dark matter is the carrot for this lab. Dark energy is the carrot for the next lab. Okay. Now, before going into it, I have a list here of the reasons why this lab is different and unique and important. First of all, spectroscopy. Any introductory sequence or lab sequence in astronomy should and usually does have a spectroscopy lab, but usually they're kind of boring. Like here's some element lamps and we're going to disperse them, and maybe you make some measurements, or maybe you just identify what element it is from the spectrum you see. This is different. This is kind of cool. Instead of looking at an emission lamp or something like that, they're going to be controlling a 6-story tall, 150-ton behemoth telescope in West Virginia and acquiring their spectra. So, that's cool. Also, we can do Doppler measurements, which you can't do with element lamps unless, I guess, you pick them up and throw them at near light speeds, or at least hundreds of kilometers at or away from the students. So actual radio spectra, actual astronomical spectra with Doppler stuff embedded that they're going to calculate and measure themselves. The second reason it's unique, it's radio. And so far, everything we've done is optical. And that's kind of standard. And everyone has an idea in their mind what an optical telescope is, what optical astronomy is. You know, most campuses have optical telescopes or an optical telescope, but most campuses don't have a radio telescope. And radio, it's the other ground-based astronomy. Everything else, you got to go to space. So you think this would be a standard thing, but campuses don't have radio telescopes because they're so huge, they're so expensive to build and maintain that they're normally not built by campuses, they're built by governments. And they're always remote because civilization hums or actually screams in the radio. And so they're always in remote locations. And so students just don't have access to them. Pros usually don't have access to them. But I've always been a big fan of radio and education. And so at Skynet, we're building it in. We got the 20 meter built in, and with the DoD, we'll soon have half a dozen radio telescopes. So anyway, in the 21st century, if you want to summarize 21st century astronomy, the common theme, it's moving out of the optical band, going multi-wavelength, because there's so much more you can learn at other wavelengths. So we're bringing them into that here. In the MWU curriculum, for those who go on to it, half the activities are radio. And here in OPIS, this was the only radio lab, but once I write lab 9, where they're going to, in lab 8, they learn about the Hubble expansion, the true nature of it. In lab 9, they're going to measure it. They'll take on-off radio spectra, kind of a fancier version of the spectra we do in this lab, and use the same H1 21 centimeter line and measure cosmological redshifts. And we'll give them information on either a Cepheid or type 1a that occurred in this each of these galaxies in the sample we give them, so they can calculate a luminosity distance. And then each of them will measure Hubble's each student in the class may do a different one, and they each get their own Hubble's constants, and we can average them all together or put them on a plot and fit a line. That's the idea. I haven't written it yet. But there will be a second radio lab, and this is where they're going to learn how to do the radio observations, and then they get to do them again. Another difference, this, as I mentioned before, this is Doppler effect. In the next lab, the understanding Hubble's law, cosmic expansion, there's also redshifts. And you've seen Hubble's plots, they're velocity versus distance, but those velocities are calculated with the Doppler equation, but they're not Doppler redshifts. They're, Doppler redshift is due to motion through space. Cosmological redshift is due to space expanding, carrying things away. And that's one of the big lessons in the next lab. And how are they to distinguish between Doppler and cosmological redshift if they haven't learned Doppler redshift? So this, here they're going to learn Doppler so they can understand the difference in the next lab. As for the flow of the lab, it's background heavy. As I've said before, you can see 1, 2, 3, 4, 5 background sections. Fortunately, a lot of this stuff is fundamental stuff. You may cover it in lecture ahead of time. Or if you do it in lab, you'll just take a little bit more time. It is background heavy. That's kind of a drawback. Another drawback is there's a little bit of trig. I've tried very carefully to keep all the other labs at high school algebra 1 level. This one does have a few sign functions. It's unavoidable. You don't have to have an understanding of trigonometry. For many, it's just a button they're going to press on their calculator that will give them this side of the triangle when they know this other stuff about it. But, geometry, it has geometry too. 3D geometry is sometimes hard to visualize. And so there's that aspect. Geometrical stuff can be hard for students to visualize, a little bit of trig. Those are the downsides. A lot of background geometry, a little bit of trig. But the plus side is once you actually get to the procedure, it goes really quick. It's really easy to do the activity itself. Okay, so that is the setup. So let's start marching through the background sections. And this is all, let's see, equipment is just the computer. The background sections, so what do we have here? Let's overview them. We have one on the Doppler effect, one on the radio 21 centimeter emission line, why we're using this. Then on the rotation curve, we have one on the spectra, and what, how to interpret them, and then one on calculating those velocities and distances from center from the spectra. And lastly, on how to convert that into a mass distribution. Okay. So I know you know this stuff, but I'll just go through it quickly so you have an example of how you may present it, like a fast version. So particularly Doppler effect, you've done this a zillion times with your students. Here's an example of a stationary object, stationary compared to our observers. It's emitting light. These circles are meant to be the crests or the troughs, or it doesn't really matter. Let's say they're the crests. And, this crest was emitted at time 1. So now it's all the way out here. And this one at time 2, 3, 4, and we're at time 5 now. And since the object's not moving, they are all, the crests will always be centered on their point of emission. And since the object's not moving, they stay all concentric. And so the observed wavelength is the same as the emitted wavelength. But if they're moving, here at time 1, it emitted, and so its crests are out here. Time 2, there's emission, and so by now at time 5, the crests are out here, but centered on point 2, which has moved. Point 3 has moved, point 4. And so the crests get piled up in the direction of motion, spread out in the opposite direction. So the wavelength that you measure is the emitted wavelength minus or plus delta lambda. Minus if it's moving towards, plus if it's moving away. And delta lambda is given by the Doppler equation, which is the emitted wavelength times the motion divided by the wave speed, in this case, the speed of light. Now, you know all that. Now, here's the subtle thing. We sometimes don't teach this in our introductory courses. In the introductory courses, we often do these simplified diagrams where something's moving directly towards you or directly away. And they have to calculate this and add or subtract. But in reality, take this for example. Here's one moving directly towards, full Doppler effect. Here's perpendicular. If it's perpendicular, no Doppler effect. In reality, it could be on some angle in between. And that will be the case here. So we have to emphasize, because it's important in this lab, what we're measuring is the component of the velocity along the line of sight. And you'll see how this is critical. Okay, that's Doppler effect. And just shout out, interrupt me at any point if I say something incorrect or confusing. Okay, now, why are we using the 21 centimeter emission line? Why not use an optical emission line? Here's the sky at optical wavelengths. It's a wraparound. The left side connects to the right, wrap it around your head. And as we can see, there are a lot of dust. They're the dust lanes. And it's blocking our view. Even the stars that we kind of see behind it are not very deep, because there's dust in there blocking the even greater number of stars beyond it. And so we're really only seeing nothing because the dust, or nearby objects, because the dust behind it is blocked even more. And so that's not going to work to probe deep into the galaxy. Now, the way it works is if the wavelength is bigger than the size of the grain, the dust grain, it passes through. If it's shorter, it doesn't. And dust grains, they have a range of sizes. The biggest ones are about a micron, which is the border between the optical and the near infrared. And so optical light is smaller than the biggest dust grains, and so some of it gets blocked and scattered by these grains. And there are all sorts of smaller grains that will scatter even shorter and shorter wavelengths. So that's why blue is preferentially scattered. It's the same reason our sky is blue, effectively. Blue is scattered out, and even red optical light, we lose a lot. You really have to go into the infrared to get past the dust barrier. But infrared is best done from space. So just keep going. Beyond the infrared, you have radio. These wavelengths are this big. They're literally, we're looking at 21 centimeters, this big. So it's a lot bigger than a micron. It goes through the galaxy unobstructed, as if the dust wasn't even there. So that's why we're using radio. But we need an emission line. In our spectrum, we need a line that we can watch it move towards or away to measure a Doppler shift. And they know about emission lines in the optical, in the infrared, and the ultraviolet due to orbital transitions, hopping from the second excited state to the first, and from the first to the ground. second to the ground, etc. They know about those kinds of Bohr optical transitions. Here in the radio, the emission line is produced differently. It all happens in the ground state. And so this 21 centimeter emission line comes from cold neutral hydrogen, which is great because that's the most abundant thing in the universe is hydrogen. Most of it's cold. Our galaxy is full of cold neutral hydrogen. So it's a great line to use. But the mechanism is called the spin flip transition. The whole thing takes place in the ground state. And so you got to think about the proton and the electron, they're little charges and they're spinning. And whenever you have a spinning charge, you have a magnetic field. If you have charge going in a loop on a circuit, you get a magnetic field. Astronomical examples, if you have an ionized accretion disk, you have charges going around, it generates a magnetic field and outflow. Even our early solar system, the proto-nebula would get these magnetic outflows. Anyway, on all scales, it's a kind of a nifty concept. Rotating, spinning charge gives you magnetic field. And I would actually bring 2 bar magnets with you. We've all played with bar magnets. They're both aligned, you try to hold them together, it's hard. They fight against each other. It takes energy. But if you flip one around, they stick together. It's easy. It's low energy. There's a way they want to be together, a way they don't. And to hold them together in the way they don't, the aligned configuration is more energy. So in the ground state, the electron can be aligned or anti-aligned with the proton. And it's a very small difference of energy. It's about, it's enough energy to produce a 21 centimeter photon. And so how's this work? The hydrogen's out there in space, something jostles into it, just bumps it gently, and transfers this tiny bit of energy that boosts the electron into this higher energy state in the ground, still all in the ground level. And then it has a half-life of 11 million years. And given such a long half-life, you may think, I'd never see anything, but there's a hell of a lot of hydrogen out there. So even despite that really long half-life, it randomly flips over and then you get 21 centimeter photon. It's enough that it's screaming bright. And so here's a map of the radio sky just in 21 centimeters. So here you're looking only at cold neutral hydrogen. And you see how compressed it is in the disk of the galaxy. And that's where the stars form. They form there in those cold hydrogen clouds. Okay, so now, again, feel free to interrupt at any point. Let's think about pointing our telescope at different places along this. These are in galactic coordinates. So here's the galactic center, and taking a spectrum. And what does the spectrum look like? And we'll start with the center, which in some ways is the easiest, but because of Sagittarius A star and other radio emitting stuff at the center, it's actually the most complicated. So you got to treat it as a bit of a special case. Imagine pointing the 20-meter telescope there and taking a spectrum. Here's an overhead view of the galaxy. And this is actually based on real data. And I usually pause and explain this a little bit. What they've done is they've taken the exact same spectra the students are going to take, and they just kind of unfolded them and figured out where all the arms are using Doppler techniques. And then they have this kind of top-down idea of where the arms are. And then this is also, it's half science, half artist. They brought in an artist to make it an artist version, but it's based on where the arms should be according to radio spectra. We did not fly out of the galaxy and turn around and take a picture. And that's what students will often think when they see this. They'll think, oh, we must have some spacecraft up there out of the plane taking a picture. It's important to emphasize our spacecraft have not even gone 1 pixel in this image. It has been reconstructed based on the exact kinds of spectra they're taking. And it's not perfect. It's probably off at the 10 or 20% level. It's kind of hard to dissect all the arms and where they exist. And so, there could be some errors in the reconstruction, but it's not bad. And we're just using for pedagogical purposes here. Here's the sun. We're not at the center. We learned that in the last lab. Great debate. And imagine, we're looking at this line of sight to the center of the galaxy. So this dashed line is us looking through the center to the other side. And I've drawn an arrow wherever we go through an arm, wherever we have hydrogen gas. And I've also drawn its motion. So this case is simple, in that everything's moving orthogonal to the line of sight. And we know in that case, there should be no Doppler shift. And so we are just measuring, where the hydrogen's being emitted. There's a little source of error there that I'll get to later. So no red shifts, no blue shifts. And what's the spectrum look like? The spectrum's actually complicated because the extra emission. So let me take a moment to explain this. All the others will get easier. Here's that emission line. So I have to fill it in. It's a broad emission line. It's not red shifted or blue shifted. But because of Sagittarius A star, the supermassive black hole at the center, and all sorts of other radio emitting stuff in that tightly packed around it, this whole thing's riding on a giant continuum. There's a ton of emission, and that emission, as it comes to us, it's also absorbed by the same hydrogen that's emitting. So we have this broad emission line, but on top of it, we have an absorption line. And we don't have this with any of the other spectra because there are no continuum emission sources. And so, I spent a little bit of time explaining this one. When we're going to measure the redshift of this one, and we can just use this point here. There's also another absorption line. This is just some cloud of gas between us and the center is moving towards us. It's blue shifted. So that one's a little bit complicated. But let's consider one that's now along the plane. The students are collecting 12 of these from 0 to 88. Once you get beyond 90, the trig gets different. So we just get 12 of them between 0 and 88 degrees longitude. And here's this one. Again, here's the one where we're looking at the center. Now we're looking off in this direction, probably 70, 80 some degrees. And again, I've put the arrows wherever we're crossing arms of the galaxy, and I've kind of indicated the direction of the flow. These are all circles, basically, is assuming a circular orbit around the galaxy. And you see there's one point that's special, and this is what makes this possible. There's going to be a point, on this side, they're moving a little bit to the left of the line of sight. This over here, farther away, a little bit to the right of the line of sight. But you have the special point where all the motion of this blob of gas is along our line of sight. And so that will be the most redshifted. As we mentioned before, it's only the component of the motion along the line of sight that gives us the Doppler shift. Like if you look at this one out here, it's almost perpendicular. So we're going to get very little Doppler shift from this one. This will be the maximally redshifted one. This one will actually come out blue shifted. Even though it has a little bit of motion away from us, we also have motion along this line of sight. And the component of our motion along this line of sight is greater than the component of its motion along the line of sight. So these far away ones will actually be blue shifted. This one here will be maximally redshifted. So here's an example of that particular line of sight. We got 3 arms here. I'm not sure which ones they are, but this one here to the right is the most redshifted. It won't always be the brightest one. I'll show you another example in a second where it's not the brightest one. Sometimes students make that mistake. They just go for the brightest one. They want to look for the one that's most to the right. And it's a little bit subjective. They can use the peak here. Maybe they want to go halfway down the peak or maybe down to the bottom. Sometimes there's some little fuzz out here that they may latch onto. I've designed the autograder to be very generous. So, for anything they would reasonably choose, it's going to work out okay. So that's the most redshifted point. Okay, so that's a little bit about the spectra and what they're going to measure. Now, to create the rotation curve, the other reason this is special is not just that the motion is completely along the line of sight, it's a right triangle between the center of the galaxy and us and this blob. And right triangles are always helpful. So here's a zoom in there. Here's the most redshifted region. Here we are. Here's the center. In the last lab, we measured our distance from the center. So we know this side of the triangle. And we know the galactic longitude because when you make the observation, you pick your galactic longitude. So given this side and the angle, you can calculate this side. The distance of the blob from the center is just 8.1 kiloparsecs times sine of the angle. Okay, so that's the easy part. That's the radial distance. The harder part is the speed. Again, rotation curve is speed versus distance. So for speed, here's another spectrum. This one's at 16 degrees. Here's the most redshifted point. It's not the brightest. As I said, it won't always be the brightest. And they're going to measure that wavelength. They're going to measure it to, you'll see 4 decimal places is the accuracy we really kind of need. And they subtract that from the emitted wavelength of cold neutral hydrogen is here. So they get their delta lambda, they divide by this number, multiply by C, and they have the relative speed of the blob compared to us. And to that, we need to know the blob speed going around the galaxy. So to that, they're going to add our speed in that direction, the component of our motion along the line of sight. Our motion around the galaxy is 220 kilometers per second. This was measured separately by looking at the Doppler shifts of surrounding galaxies. And we realized we have a net motion here. And so our motion along this line of sight is 220 sine L. That's kind of the hardest part. And so they do this for their 12 lines of sight, and they plot it, and we'll see examples of what that looks like, but that's the rotation curve. The last bit, again, I said there's a lot of background here, so you may want to spread it out. You may want to cover some of this stuff in lecture if you have that opportunity. But turning the rotation curve into a mass. And I start with the simple example of Earth going around the sun. If the sun's mass were to suddenly become 0, we would fly off at whatever our current trajectory is. If the mass were to suddenly become infinity, we would move off our orbit and quickly just whoop, right into the sun. So the fact that we're in a circular orbit at a certain distance, moving at a certain speed, it's because of the mass that's inside. We move at that speed at that distance because of the mass. And you saw, if I were to change the mass of the sun, we would not be moving in the way that we are. And Newton sorted out what that is. It's a function of not just the mass at the center, but all the mass that's enclosed in your orbit. Suppose we're talking about the galaxy. Outside your orbit, there's mass, both on your side and the other side. But Newton showed that all cancels. You may be strongly attracted to mass here, but there's even more mass on the other side. It's farther away, but there's more of it in the same angle. It cancels out. So really, your motion is all about the enclosed mass. And Newton showed the enclosed mass is just v squared r divided by g. And in the rotation curve, they measured v. They measured the distance from the center. And that's just Newton's constant, so you can calculate enclosed mass. For solving for v, here's the case of the solar system. In the solar system, all the mass is in the sun. So it's a constant. And so your velocity is just some constant divided by distance from sun, the square root, 1 over r to the 1/2. And that's what we call a Keplerian rotation curve. Neptune orbits the sun more slowly, Mercury orbits it more quickly. With galaxies, not all the mass is concentrated at the center. It can be spread out. It's always spread out, but I would describe it, I wouldn't give the answer away to the students. I'd say in some galaxies, the mass is spread out. And the farther out you go, you have more enclosed mass. And if it's increasing in some galaxies, it increases the same rate as the radius. And so these cancel out and the velocity is just constant. We call that a flat rotation curve. So it ramps up for a little bit, but then it holds steady. I mean, pretty much all galaxies are this way, but I wouldn't say that because that's what they're going to measure for our galaxy. Okay, we're done with the background. Let me just pause. That was a lot of information. I know you know this stuff, but it's a lot for students to absorb as well. So either you do some of it in lecture or you do it all in lab, but fortunately the procedure part's quick. So I'll stop. Any questions, thoughts? Okay, well, let's do the procedure. Here, this is putting in the observations. We talked about that last time, how to do that. Our 20-meter radio telescope that will soon be half a dozen. And the interface will be very different, so I'll have to rewrite the instructions once we have multiple telescopes. But anyway, They've now collected their 12 spectra. And as I said, I encourage you to try 5 seconds, not the 2 seconds written here. We'll see if that works better. And then 2 procedure sections, one where they're going to make the rotation curve, one where they're going to do the enclosed mass, which is weighing the galaxy. So for the rotation curve, we give them this table. Here's the longitude of their dozen observations. Here's the wavelength of their most redshifted point. They're going to calculate the relative speed using the Doppler equation, the sun's motion along that line of sight, add them together for the total speed of that blob going around the galaxy, and then they calculate the distance from the center. And there's little hints on where this was covered and the information they need to do these calculations. They're all here. They don't have to go rifle through the background sections looking for everything. This will help them along their way. But we also provide them with the spreadsheet. Instead of doing all this by hand, we've been teaching spreadsheet skills. So let me just do this for you here. Here are the 12 galactic longitudes. Now, in spreadsheets, they use radians when they do their trig functions. So we have them put it into radians. And so it's this divided by 180 times pi. You got to close the parentheses. And once they do that, again, you know these things, but I'm just going to show you. Drag it down, and okay, now everything's in radians. Here they type in their measured wavelengths. I don't know. I'm just going to put in a few numbers that I don't even. I don't know if they're good numbers or not, and you keep going. The relative speed. 2 ways you could do this. I'm going to show you the way that we would do it, and then the way you probably want your students to do it. Doppler equation is the observed wavelength minus the emitted wavelength. I have that over here in the table. All the constants are over here, divided by the emitted wavelength times the speed of light. Now, that one's right, but if I drag it down, it'll be wrong because it will use the next wavelength, but it also drag the constants. For these constants, for them to stay on K3 and K2, you have to put a little $sign between the letter and the number. Then if you do that, the constants will stay put, but it will use the different wavelengths. Now that may be too complicated for the students, so they could also just use this table and type the numbers in. 21.1061 and speed of light 300,000. Okay, so you do this and you'll get the same answers, and they may not have had to code, they didn't have to go through the Excel coding. Total speed is the relative speed. Oops, my bad. Now this is the sun speed. Sun speed is 220 times sine of L. Drag those down. Total speed is the relative speed plus the sun speed along that line of sight. Drag those down. And then the speed of that blob in the right triangle is just the 8.1 kiloparsecs that we measured times sine of L. And of course, they would have all the numbers and they'd drag it all the way down to here. But what you end up with are speeds versus distances. And let me go into answer key mode so you can see what this looks like. So in answer key mode, the table is a lot messier. But before that, what do we have? We have a well, I skipped over a few steps. I didn't tell you how they make the measurements, so let's do that first. That's the table where they're doing their calculations, but how do they make these measurements? I guess I'm going to go a couple minutes over. I apologize. Not too much over. This won't be much longer. So here's the link to our new spectrum tool. I have the old one here. Here's the new one. And actually, let's start with Skynet. Go to radio observing. Here, I'll grab one of them. This is galactic longitude 8. Oh, that one's ready. I got to do one that's been archived. Galactic longitude 8. Here it is. And what you want to do is go to calibrated spectrum, right click, save link as. Should save it as a text file. Again, in Skynet 2, we'll have our own stuff here. We won't be using the Greenbanks page. We just grab the calibrated spectrum and then load it into the tool. Having problems with the something here. I saw this yesterday too. Let's try this again. Oh, for some reason, when this downloaded, didn't download with the right extension. Let's try it now. There we go. In the old tool, I think we taught it to not worry and load it anyway. So this is something we'll have to improve. But here's galactic longitude 8. Here's the most redshifted point right there, 21.1156. They'll need 4 decimal places, and that's what they're sticking in the table. So they download it, they measure it here. Yeah, okay. And then once they have those, yeah, let me bring the lab back up. Sign their name. We have them load a sample plot. And for each calculation, we have them do an example. And then they go back to the graphing tool. Go to the new one here. And then they go back to the simple curve tool, and they're going to do a plot of velocity versus distance from the center from their 12 data points. And it looks something like this, where it ramps up and it's pretty flat. We ask them, is our galaxy's rotation curve Keplerian or flat? It's flat. Does that mean the matter is concentrated at the center, spread throughout the disk? It's spread throughout the disk. Discuss significant sources of error. The biggest one's determining the wavelength of the most redshifted emission, given the spectra can be kind of noisy. It's actually not noise, it's messy. The data's messy. And sometimes peaks blur together, can be a little tricky. Another reason is maybe that special point, the most redshifted region, falls between arms of the galaxy. So that could be a source of error. And the third one, which very few students get, we've totally ignored the Earth's motion around the sun, which is about 30 kilometer per second effect. And we just leave that out of the simple exercise and treat it as a source of error. If they get 2 of the 3, we give them full credit. So they have the rotation curve. The last thing is weighing it. And so they're going to calculate the enclosed mass. We can do that in the spreadsheet. Again, it is equal to V squared times the radius divided by the gravitational constant. Now our velocities are in kilometers per second, our radius is in kiloparsec. G is usually in the MKS system. That's a nightmare conversion for some students. So we've calculated G in this system with kilometers per second, kiloparsecs, and billions of solar masses. And it's just 4302. They can enter that, and then they have their enclosed masses. So the farther out you go, well, it depends on what numbers are here, the enclosed mass increases. And we throw in 2 points, the LMC and the SMC, so we can get out beyond the visible disk. So sample calculation, here's a picture of the LMC and SMC. They calculate enclosed mass out to them. Then going to the curve site, they're going to plot enclosed mass versus radius. Here are their 12 measurements, and here's the SMC or LMC and SMC. And then and this is the very end. WebAssign sometimes cuts off the bottom. You got to close and reopen. So we ask them these leading questions. Using your graph, estimate the mass of our galaxy out to the sun's radius. So the one at 8.1, and in the, it will come out something like 70 gigasolar masses. And next time I edit this, wherever I have giga solar masses, the G is they get confused between giga and Newton's constant. So I'm going to actually write out billions of solar masses instead of gigasolar masses. Then we ask them, we say in lab 6, we said our galaxy is 34 kiloparsecs in diameter, so 17 kiloparsec radius. What's the enclosed mass out to there? So they go out to 17, they estimate something in the 200s. And then using the graph, estimate the enclosed mass out to the SMC at 61, it's something like 900. And then we have them subtract how much mass enclosed out to the SMC minus the mass enclosed out to the edge of the visible galaxy. And that's how much mass is out beyond the edge of the visible galaxy. It's like 600, almost 700. And then we ask them to compare it to the mass within the visible galaxy. Is the mass outside the visible part less or more the mass inside the visible part? And it's more. And so does that mean, and then we remind them that the LMC and SMC themselves don't have very much mass. So that's not the reason. So within 61 kiloparsecs, is our galaxy mostly visible matter, like stars and gas, or mostly dark matter? It's mostly dark matter. Then we just have them go into Wikipedia and learn some things about dark matter, what dark matter candidates may be, and write a little short answer there. So that's the lab. Questions, comments? I don't feel I gave it the best presentation, but it's once you get through the background, and again, a lot of that stuff you're teaching anyway in an introductory astronomy lecture, the execution is pretty easy. And the students find it cool that they've rediscovered, with a lot of guidance and help and some extra numbers, they didn't measure dark matter.
If we can just get them to read the instructions.
Yeah. Well, the trick is to get them to read the background. The instructions aren't that bad, right? But they always skip the background sections. And so that becomes incumbent upon you to kind of present it. I tried with the video. I gave them a video so they don't have to read. They can just listen. But yeah.
No, but I had a student, Brett. Please go ahead.
So we said there is a dark matter by comparing the visible versus radio, or how is that?
So here we're using the radio to measure the enclosed mass out to different distances, and so we're just comparing the mass out to the Magellanic Clouds, the mass within the Magellanic Clouds, the mass within the visible edge of the galaxy. All the measurements are done in radio, but in the previous lab 6, we measured the size of the galaxy. So we know the visible part goes out to a radius of 17 kiloparsecs. So from the previous lab, we know the visible part of our galaxy, if we look, with our eyes, the galaxy only appears to be this big, yet the mass continues to increase as we go beyond the visible edge.
Okay.
In reality, our galaxy is primarily a giant ball of dark matter. And the normal matter is settled down to the middle and it's making this little spiral. But we're living in a giant dark matter halo.
But the hydrogen is everywhere.
The hydrogen is just in our galaxy. It's not out in the halo.
Okay.
Yep.
But we recorded the hydrogen 21 centimeter. So that is sensing the hydrogen.
Yeah.
And then we measure the size of the galaxy. This means that that hydrogen was covering the galaxy.
All that we did was measure the galaxy, the hydrogen in the galaxy for these 12 lines of sight, and those are these points. For these two, we just gave them. You have to use different techniques to figure out the speed of motion of the Magellanic Clouds and the radius. So these were not measured by the students or in the same way.
Oh, okay,
So it's a little bit of a cheat, but
okay,
by adding these 2 points in, you can really ask them probing questions about dark matter.
okay.
So what they measured
Appreciate it.
with
I
their
have- Mhm.
what they measured with their data was the mass of the galaxy on these scales. And then we say, oh, there's also this stuff, and then they use the same physics, same equations, and realize, oh wow, there's something we can't see out there, and a lot of it.
Okay, great. Thank you. I have to leave for my next class. Appreciate it.
Apologies for running over. Ian, someone's at my door. I got doing a maintenance thing here, so I need to
You know
go.
what? I'm gonna leave you alone, Dan. Thanks for the information today.
Okay, and see you, Anna.